Hello, am I audible? Hi, Momin. Can you confirm that? Am I audible? Am I audible? Okay, I think I am audible. So let's start this live session. So this is live session for sixth week, and I'll be discussing some problems related to the course material of the sixth week. So the most of the problems are related to the beta and gamma function and evaluating integrals using Leibniz rule and some application of double integrals for finding area and volumes and some specific conditions. Okay, let's start with the first problem. So first problem, we have to find, okay, so there is a one equation and we have to find the value of alpha and gamma depending on m and n. Okay, so this is problem based on the beta function. Okay, let's recall what is beta function. Okay, so what is beta function? So beta of m comma n is equal to integral from 0 to 1 of x minus 1 to the power m x to the power m and 1 minus x to the power n dx. Okay, okay, so it's m minus 1 and minus 1. This is the definition of beta function, and we have been given that beta of m plus 1 comma n plus beta of m comma n plus 1 is equal to beta of alpha comma gamma, and we have to find the values of alpha comma gamma. Okay, so let's find out what is this, and we just apply the definition of this integral. This is 0 to 1 of x to the power m and 1 minus x to the power n minus 1 dx plus the second integral is 0 to 1 x to the power m minus 1 and 1 minus x to the power n dx. Okay, now we can add these integral 0 to 1 and we'll take x to the power m minus 1 and 1 minus x to the power n minus 1 common. So what do we have in bracket? We will left x plus 1 minus x, right, dx. And what is that? 0 to 1 x to the power m minus 1 and 1 minus x to the power n minus 1 dx, which is precisely equal to beta of m comma n. Okay, now therefore the value of alpha is m and the value of gamma is n. This implies alpha is equal to m and gamma is equal to n. Okay, therefore the option D is correct. Okay, so if there are any problems, you can ask me. Okay, so if there are no other problems, let's move to the second problem. And this is, so here h is given to be a constant and we have to find the value of this integral in terms of gamma function. Okay, So what is this integral? This is 0 to infinity x to the power n minus 1 e to the power minus h square x square. Okay. Okay, now if you have to find value of this integral in terms of gamma function, note that in the integrand of the gamma function contain a negative of exponential, which is e to the power minus t. Okay, so we have to make somehow this h square times x square. We have to change the variable. Okay, so let's put h square x square equal to t. Okay, because this h is constant, so what we have 2x h square dx is equal to dt. Okay, this integral is equal to the 0 to infinity. Now instead of x, but we will put, okay, note that because h square x square is equal to t, therefore x is equal to t to the power half divided by h, right? So we have t to the power half over h to the power n minus 1 and e to the power minus t, and then what is dx? Dx is dt divided by twice x of h square. Okay, so what we have here is 0 to infinity. Okay, note that we can take h to the power n minus 1 outside, so this will just become h to the power n plus 1 and t to the power half times n minus 1, and okay, so note that this x can again be written as root of t, right? Okay, so what can we write? Dx, this is dt divided by twice h squared times x. So what is x? Is t to the power half into h, which is exactly equal to dt divided by twice h root of t. Okay, okay, now this 2 also comes out, and this root t, because this is t to the power half, you just subtract this half from here, and this is e to the power minus t dt. Okay, so what do we have? Half 2 to the power h, so 2 times h to the n, integral from 0 to infinity. So this will turn out to be t to the power n by 2 and minus half, which becomes 1. So e to the power minus t dt, right? Now by the definition of gamma function, this particular quantity will become gamma of n by 2, right? This is gamma of n by 2, and this is divided by 2 to the power h, twice of h to the power n. Okay, therefore the correct answer is B. Okay, let's go to the third problem. Okay, so again we have to find the value of this integral in form of, in terms of gamma function. Okay, so we'll just change the variable so that it look like gamma function. Okay, so for gamma function we must have an exponential, and the limit must be from 0 to infinity. Okay, so we just substitute ln of 1 by x to some exponential. Okay, let's see. This integral is from 0 to 1 x to the power p minus 1. Now ln of 1 by x to the power m minus 1. Okay, dx. Okay, let's put ln of 1 by x as our new variable t. Okay, so if ln of 1 by x is t, then what is x? X is e to the power minus t, and therefore dx must be negative of e to the power minus t dt, right? Okay, now note that when x becomes 0, this integral, this limit will become infinity. When x become 1, ln of 1 is 0, so this is infinity to 0. Okay, now instead of x, what we will do, we'll put e to the power minus t, so e to the power minus t to the power p minus 1, and ln of 1 by x we have taken to t, so t to the power m minus 1. What is dx? It's negative of e to the power minus t dt. Okay, so this can be written as integral from 0 to infinity. This minus will, because of this minus negative sign, we can change the, reverse the order of the integration. This becomes from 0 to infinity. Okay, now we have one more e to the power minus t, so this will become e to the power minus t to the power p, right? And t to the power m minus 1 dt. Okay, so now note that this is not in the form of gamma function because we require e to the power minus t, but a factor of p is there, so we'll again change the variable. Okay, so what we do, let's put tp equal to some y. Okay, when tp is y, you have p times dt is dy, right? Okay, so now this will become 0 to infinity. Now instead of tp we have y, and from here what t is, t must be y over p. So instead of t we will put y over p, so y over p to the power m minus 1 dt. Okay, so this will become 0 to infinity, e to the power minus y to the power m dt, right? And okay, instead of dt we have to write dt in terms of dy. So what is dt? This is dy by p. So dy by p. Okay, so now what we have, we can again take p outside, so this is p to the power m integral from 0 to infinity e to the power minus y and y to the power m minus 1 dy. Okay, now you can see that this integral is our gamma function, so we can write this as gamma of m divided by p to the power m. Okay, so this is our correct answer. The correct option is a. Okay, so let's move to the next problem. Now, in this problem, we have to find the value of this given integral by using Leibniz rule. Okay, so in what is Leibniz rule? So in Leibniz rule, what do we do? If our integral is a function of some parameter, then we first differentiate the function and then evaluate the integral and then again find the value of. So let me show you how this can be done. Okay, note that the integral which we have is 0 to infinity e to the power minus x divided by x. In bracket we have this a minus 1 by x plus 1 by x times e to the power minus of ax and dx. Okay, now note that this variable of integration is x. So when you integrate with respect to x, this value of the integral will depend on this constant a. So this here a is a constant. Therefore, this integral value of this integral actually depends on a. So this is a function of a. Let's call it phi of a. Okay. Now we have to find this phi of a. Now because this is an improper integral and sometimes it's difficult to calculate improper integral directly. So Leibniz rule give us a way to calculate some particular indefinite integral, improper integrals. So what we do, uh, so Leibniz rule say that we can differentiate this function with respect to a in a way that how we differentiate. So this we are differentiating it with respect to a. That is, we are differentiating d by dA of phi a. Okay. So the Leibniz rule says that while differentiating this integral, you can take this derivative inside the integral sign. Okay, that is, instead of integrating the integral first, you can differentiate the function or the integrand first with respect to a. So that is, this will be just a partial derivative because the integrand is a function of two variables a comma x. So we can just differentiate the integrand with respect to a. Okay, so this is equal to, so we can take this derivative sign inside and this will become a partial derivative because there are two variables. Okay, this is the Leibniz rule. It says that we can take this derivative inside the integral. Now, okay, now what do we have? This integral, because now we can differentiate this integral in respect to a. So we get e to the power minus x divided by x. Okay, now differentiate the integral with respect to a. This is partial derivative. Okay, this a will become 1. This 1 by x will be treated as constant, so its derivative becomes 0. Now differentiate e to the power minus ax with respect to x. No, with respect to a. So the minus x will get outside by the chain rule. So what do we have? This is e to the power minus ax. Okay, dx. Okay, so now we get this integral. Now still it is not clear that how do we evaluate this integral. Okay, so now because we have differentiated this integral, the given integral once, why not do it twice? Okay, so we can again apply Leibniz rule. So again we have an improper integral which depends on a. So this is a function of a, and we can again differentiate this function. That is, we can find the double derivative by Leibniz rule. So that is d by dA of phi prime a. Okay, what is that? That will be the integral from 0 to infinity. We can take this d by dA inside of the integral and this will become the partial derivative. Okay, so e to the power minus x by x 1 minus e to the power minus ax dx. Okay, okay, what do we get after if we differentiate this again? So 0 to infinity. Okay, again this e to the power minus x by x will be treated as constant because we are differentiating with respect to a. In the bracket, but we have this 1, this derivative will become 0, and the derivative of this e to the power minus x will become minus x times e to the power minus ax. Okay, so this will become just x times e to the power minus ax dx. Okay, now this x we can cancel, so this is from integral from 0 to infinity e to the power minus of x in bracket a plus 1 dx. Now you can see that this integral, okay, we can evaluate this integral easily because this is an exponential function. Okay, okay, so what is the integral of this function? Integral of exponential function is just itself, right? Thus we have to divide by this a plus 1, the factor of a plus 1, come with a minus sign, and then take the limit from 0 to infinity, right? So what do we have? What do we get after taking this limit from 0 to infinity? Note that when you take put we take limit up to infinity of this exponential function, because this is e to the power minus ax. This, in the limiting process, this will become 0, and then we have another minus sign here. So it will turn out to be 1 over a plus 1, right? Why? Because the exponential function will become 1 when you put the lower limit 0. Okay, so now what do we have? Now this implies that the twice derivative of a is equal to 1 over a plus 1. Okay, now it's a simple easy differential equation. You can integrate both sides 2 times to get the value of the function. Okay, so what we'll do, integrate both sides with respect to a, we'll get phi prime a equal to the log of a plus 1, right, plus some constant, let's call it c1. Now you can integrate twice also. Integrate again. If you integrate again with respect to a, you will get phi of a is equal to the integral dA divided by, so integral of log of a plus 1 dA plus c1 times a plus another constant of integration which we call c2. Okay, now what is the integration of log of a plus 1? It will come as a plus 1 times log of a plus 1 minus a, and we have this c1a plus c2. Okay, so we have our value of our integral, but there are two constants, this c1 and c2. So we have to determine the values of c1 and c2. Okay, how do we find the values of c1 and c2? We'll use these equations. So c1 first appears in this equation and c2 is first appears in this second equation. Okay, so what we'll do, we put a equal to 0. So if you put a equal to 0 in the first equation, you will get ln of 1, which is 0. C1 is exactly equal to the derivative of phi at 0. Okay, so what was the derivative of phi at a? So this was phi prime a. Okay, now note that if you put a equal to 0 in this equation, what do you get? Okay, e to the power minus ax, if you put 0, it will become 1, so this will become 0. Okay, so phi prime 0 is 0, so therefore c1 is 0. Now put a equal to 0 in the second equation. What we get when you put a equal to 0, this log will become 0. Okay, we have shown that c1 is already 0, so we get c2 minus a. So phi of 0 is equal to c2 minus a. So what is phi of 0? So this was our phi function. If you put 0 here, you'll get again 0. Okay, this a is not here because we are putting a equal to 0, right? So this a is not here. This is just c2. Okay, so phi of 0 is c2, which is again 0. So these values of c1 and c2 will become 0, and hence phi of a is equal to a plus 1 log of a plus 1 and minus a, and therefore the correct option is D. Okay, so there is again another in the question number 5. There is again another integral, improper integral, and we have to find its value using the Leibniz rule. Okay, if there are any doubts still here, you can ask. Okay, so if there are no doubts, let's move to the fifth problem, which is again you have to find the value of this improper integral using Leibniz rule. So what is our integral here? This is integral from 0 to 1 x to the power n minus 1 divided by 3 times log x. Okay, so 3 times ln x and dx. Again, note that this integral will depend on the value of n, because we after getting the after integrating with respect to x, this will depend only on n. So this is actually a function of n, so we can call it phi of n. Okay, so now we'll apply Leibniz rule. So what Leibniz rule says, you can, okay, so we just differentiate this function with respect to n, that is dy dx of phi n, which is phi prime n. And this Leibniz rule says that this integral, this d by dx sign, which it can be taken inside the integral, this is equal to 0 to 1, but it will become the partial derivative with respect to n, right? Okay, so this is x to the power n minus 1 divided by log x dx. Okay, so we have to differentiate this integrand with respect to n. So what we will get? The integral from 0 to 1. Okay, how do we differentiate x to the power n with respect to x? Note that we are differentiating x to the power n with respect to n, not with respect to x. So x is a constant. So when x is a constant, this will become an exponential function with the base x. So when base is x of an exponential function, the derivative is itself x to the power n, and we have to multiply it by log of x. Okay. Now there we have log of x in the denominator also, so they will cancel with each other, and this will become just 0 to 1, integral from 0 to 1 x to the power n dx. Okay, so actually this is 3 times log x, so we have a 3 also. Okay, now we can integrate it, right, easily. What is the integration of x to the power n? It's x to the power n plus 1 divided by n plus 1, and the 3 we always have here, and we have to take limit from 0 to 1. Okay, therefore the phi prime of n is equal to 1 over 3 times n plus 1. Okay, this is our derivative of phi with respect to n. Now we can integrate this with respect to n to get the function phi n. Okay, so after integrating, what we have, phi of n is equal to integral with respect to n divided by 3 times n plus 1. Okay, so this integral is 1 by 3 the log of n plus 1 plus a constant c1. Okay, so how do we find the value of c1? Just put n equal to 0, phi of 0. When you put n equal to 0, this will become a log of 1. Okay, but phi of 0 can also be calculated from this given integral, because this is the definition of phi of n. So just put n equal to 0. So when you put n equal to 0, this x to the power n will become 1. So 1 minus 1 is 0, right? You can see that this phi of 0 from 0 to 1, x to the power 0 minus 1 divided by log x 3 times dx. This will become just 0, right? Because x to the power 0 is 1. Therefore, this c1 will become 0, and hence phi of n is is equal to 1 by 3 log of n plus 1. So what is the correct answer? B is correct answer. Okay. So are there any questions regarding this problem or any other problem? Okay, so if there are no other problems, let's move to the next problem. Okay, so the next problem is based on uh, these are some applications of the double integral. Okay, so by this double integral, we can get area of some region, a two-dimensional region, or the volume of some surface below the graph of the surface. Okay, below the graph or below the surface. So in this problem, we have to find the volume of the region bounded by this function z equal to 6 minus 5 times x square, which is bounded by these planes y equal to x, y equal to 1, x equal to 0, and the xy plane. Okay. So let's first draw the domain of this function. Okay. So this okay. So this is our xy plane. Okay. So this the do the domain of the function is okay. So this is bounded by this z equal to 6 minus 5 x square. So this is surface in xyz coordinates in the 3 dimension, and we are taking the projection in the plane, and in the plane we have this line y equal to x because the region is bounded by line y equal to x. We have line this y equal to 1. This is our line y equal to 0, and we also have x equal to 0. So what is x equal to 0? Okay, so this is not line y equal to 1. So this is line y equal to 1. Okay, so this is line y equal to 1. This is line y equal to 0, and this is line x equal to 0. Okay, so this is our projection of this region in xy plane, and we have to integrate this function over this region, okay, to find its volume. So what is the volume? Let's call this region as D. The volume which we define as V is precisely the double integral over this D of this function 6 minus 5x square, okay, and we are integrating this over the domain dy dx. Okay, so for this particular domain we'll put the limits of x and y. Okay, so now note that first we integrate this function with respect to y, or first with respect to x, it doesn't matter. Okay, so let's first integrate this with respect to x first. Okay, and then we will integrate this with respect to y, so dx and dy. Okay, so now first we have to find the limits of x by keeping y constant. So if y is constant, so x varies from, okay, so this is some y equal to constant. Let's say this y equal to c, this is constant. Now note that x varies from 0 to this line y equal to x. So what is the limit of x? X varies from 0 to y, and then y varies from 0 to 1, right? So these are limits of integration. Now we can find our volume by just integrating this function one by one. First integrate this with respect to x. What do we get? 6x 5x cubed by 3, and we have to take limits from 0 to y, and then we have to integrate with respect to y also. Okay, so what do we get? Integral from 0 to 1. So we have to put upper and this lower limit. If you get put y, then we have 6y minus 5y cubed by 3, and when you put 0 you will get 0. So we have to integrate this with respect to y. Okay, Now integrate with respect to y. So what we have from 0, integral from 0 to 1. So this will become 6y square by 2, which is 3y square minus 5 times y to the power 4 by 4. So this is 5 by 12 y to the power 4, right? This is our integral, and we have to find values from 0 to 1. Okay. So what are these? When you put 1, you'll get 3 minus 5 by 12. When you put 0, so what is 1 by 12? Okay, so correct answer is B. Okay, so any questions regarding this problem? So the next set of problems are based on these double integral or the applications of double integral. Okay. Okay. So let's move to the next problem. We have to find the value of this given integral. Okay, so again, this is a double integral. Okay. So for finding such integral or any double integral, first always observe what is our domain of integration. Domain of integration means first draw the domain of integration in xy plane, and by that I mean that you have to find the part of the plane where your x and y can vary. Okay, so for example, here y can lie between x to the power 1/3 and 1, and then x lies between 1 and 0. Okay, so now note that the sometime okay, so we can find out the value of this integral by integrating this function one by one, first with respect to y and then with respect to x. But sometimes it is beneficial to change the order of the integration. Okay, that is, first do the integration with respect to x, then do the integration with respect to y. Okay, so if you change the order of the integration, these limits of the integration will also change. Okay, so let's see how these limits of integration will change. Okay, for that we will just draw this region in the xy plane. What is that region in the xy plane? For that we have to draw. Okay, so this is our line y equal to 1, this is our line x equal to 1. Okay, then we always have this y equal to 0, and this is our x equal to 0. And then the next the y is at most x to the power 1/3. So when y is equal to x to the power 1/3, so that is the graph of function y equal to x power 1 by 3. This is our graph. Let's say that it looks like this approximately. Okay, and then note that because while y varies from 1 to, oh no, so there's some little bit mistake here. Okay, so upper limit is 1 and the lower limit is x to the power 1/3. Okay. The lower limit is x to the power 1/3 and upper limit is 1. Okay, so y varies between this. This is the range of y. Okay, so this is the function of x equal to 1 by 3, and this is y equal to, okay, so this is the region of integration. Why? Because if you fix x, and you can see that if this is x equal to constant, you can fix, then you can see that y varies from x to the power 1 by 3 to y equal to 1, and then x will vary from 0 to 1. So this is our area of integration or the domain of integration. Now we'll change this integration, the order of integration. Okay, so this is 0 to 1, and then x to the power 1/3 to 1, e to the power y by y to the power 4, dy by dx. Okay. Okay, instead of finding this integral, what we will do, we'll find another integral which is same as this given integral, but the order of the integration is reverse. Okay, first we will integrate with respect to x, then we will integrate with respect to y, and for that we have to find these limits of integration, and the limit of integration for this particular region, keeping in mind, because this is the region of integration, the shaded part, which where we are integrating. Okay, so note that first we are integrating with respect to x, therefore y is constant. Okay, so we have just draw some y equal to constant line. Let's say this is our y equal to constant. Okay, so now note that when y is constant, x varies from 0 to, this is x equal to 0, this line is x equal to 0, so x varies from 0 to this graph of this function. Okay, so what is this graph? The graph is x is equal to y cube, right? Because y is equal to x to the power 1 by 3. So x varies from 0 to y cube. And then x vary, and then we have y, and when y varies from 0 to 1. So these are new limits of integration with respect to the same region of integration. Okay. Now note that we are integrating first with respect to x, therefore this will be treated as constant. So we'll just take out, keep it outside. So this will become 0 to 1 and e to the power y power 4. And then we have this integral dx dy from 0 to y cube. So we have to integrate this with respect to first. Okay. So this will become 0 to 1. What is the integral of a constant from 0 to y cube? It's just y cube. And then we have e to the power y power 4 and dy. Now note that the evaluation of this integral is easier than the previous one, because we have a y cube times e to the power y power 4, and that can be evaluated by just changing the limits of integration, or by changing the variable of integration. Okay, how that can be done? Just put y to the power 4 is equal to t, then 4 times y cube dy will become dt. Okay, so you can replace this value by dt by 4, so this will become e to the power t dt by 4. Okay, now the limit of integration will be from 0 to 1 only. Why? Because when y is 0, t is 0, when y is 1, t is also 1. So now this integral can be easily evaluated. This is 1 by 4 of e to the power t, where limit taken from 0 to 1, right? Which is equal to 1 by 4 e minus 1, right? Okay, so that is the first option is correct. Okay, so any questions regarding this problem with the calculation of the integral or with the determination of the domain of the integral? If there are any questions, I can answer that. Okay, so if there are no other questions, let's move to the next problem. Okay, so again in the next problem is some equation between integral is given, and you have to find the values of p, q, r, and s. Okay. Okay, for this, note that in the left hand side, the order of the integration is dy dx. So first we are integrating with respect to y, and then we are integrating with respect to x. But on the right hand side, the order of the integration is dx dy. That is, we are first integrating with respect to x, and then we are integrating with respect to y. Okay. So what we will do, we will just change the order of the integration, and we will see what is right hand side is coming to determine the values of this p, q, r, and s. Okay. Okay, for that we have to draw the region of integration. Okay, so again, for drawing region of integration, first find the limits of. Okay, so note that y is lies between 2x minus 1 and x square. Okay, so y lies between x square and 2x minus 1, and then x lies between 0 and 1. So 1 and 0. So let's find out the area of or region of integration. For that, we will draw these graphs of these functions y equal to x square and y equal to 2x minus 1. Okay, so let's say this is our y-axis, this is our x-axis, and what is y equal to x square? It's a parabola like this, right? Or like this. So let's say this is our graph y equal to x square. Okay, now draw the second graph, which is y equal to 2x minus 1, and that is a straight line. Note that just find out from where, find out 2 points from where this passes through. Okay, you just put x equal to 0, you will get y equal to minus 1. So let's say this is minus 1 comma 0 point, or 0 comma minus 1 point. And then if you put x equal to 1, then you will get y equal to 1. Okay, let's say there is some point x equal to 1 and y equal to 1. So let's assume that this is our point 1 comma 1. So this is a line which passes through these 2 points. Okay, so it's looking like a curve. Okay. Okay, assume that this line is straight. Now our y varies. So when x is constant, y varies from the line 2x minus 1 to the graph x square. So this is the our area of integration. Okay, let me draw it clearly. So what is our area of integration? So we have some line, and then we have some graph y equal to x square, like this. Okay, let's assume that this is our 1 comma 1 point, and this is our 0 comma minus 1 point, and this is y equal to x square, this is y equal to 2x minus 1, and this is our area of integration. Okay, so now what we will do, we'll change the order of the integration. First we will integrate with respect to x, and then with respect to y. Because we are integrating first with respect to x, then y we have to keep constant. And for that, what we will do, we will divide this area of integration into two parts. Okay, the first part is this, and the second part is this. So let's call it d1 and let's call it d2. Okay, therefore our given integral, which is first dy dx, and then limits from 2x minus 1 to x square 0 to 1, this will break into two parts. Two parts mean the first region d1 of dx dy plus the second region d2 dx dy. Okay, and now we have to just find the limits of the integration. Okay, so what are limits of the integration for the first part, the d1? Okay, so let's write this integral equal to, okay, note that in d1, when you fix y equal to constant, or let's say this is our line y equal to constant, this is our line y equal to constant. Okay, so in the region d1, y varies from, or x, because y is constant, x varies from x equal to 0 to this line, which is y plus 1 divided by 2. Okay, and then what are limits of y? Note that limits of y are from -1 to 0, dx dy. Okay, so what is the value of the integral for the second region? Okay, again do the same trick, keep y constant. So if you keep y equal to constant, let's say this is our line y equal to constant. In that case, x varies from, again, the graph of the function to the line, right? The graph of y equal to x square. Now for that, x varies from, because the graph is y equal to x square, so x varies from under root y to our line, which is y plus 1 divided by 2. Okay, and then x varies from 0 to 1, right? Because this is point is our 1 comma 1. So these are limits of integration. Now we can compare these integral which are given here, and then we'll get our values of p, q, r, and s. Okay, compare these two integrals. When you compare these two integral, you will get, so this will imply that p is equal to 0, q is equal to -1, r is equal to 1, and s is equal to 0, right? So p is equal to 0, q is equal to -1. Okay, so that is the option B is correct. Okay, so for finding values of p, q, r, and s, we have not calculated the exact values of these integral. Just change the order of the integration, determine the region of the integration for that, and rewrite your given integral in term by changing the order of the integration, and you will, by comparing these integral, you will get your values of p, q, r, and s. Okay, this exercise was given, this exercise was designed so that you can change the order of the integration to find the value of the integral. Okay, sometimes it is better to change the order of the integration. Okay, so are there any questions regarding to this problem or any other problem? Okay, so if there are no other questions, we will stop our live session at this point, and we will again meet next week with another set of problem based on the lectures videos of the next week.